I think we should get started in here. Okay. Good morning. I'm have to talk in this low voice just because I think I've been coughing the past few days and doesn't seem to get better. I think talking in this low tone kind of avoids triggering it too much. So if I cough a little bit here or there, I apologize for that. I'll do my best not to do that. We'll see. So this is our Thursday, week 4. Thursday, week 4. Okay. So there are a few things that we need to logistically to remind folks. Number one, our quiz quiz 4 is tomorrow, right? So make sure we finish the quiz tomorrow. And then our lab 3 was done yesterday, and also we have a PA due this Sunday, or PA due this Sunday. So 3 things, 2 things are still kind of pending, right? And next week we have a lab next week, and there's no quiz next week. And then we have the final exam on Saturday of next week. So that's the logistic stuff. Are there any questions about the logistics? All right. So the plan for today is we'll finish steganography, right? Last time we did a quick demo of steganography, what it does, and today we will kind of find a nuanced way to solving the problem, okay? So, which is to use bitwise operation. A quick reminder of what steganography is, right, here. So you have a secret image. Is a rabbit. We want to hide the rabbit in the hat. So how should we do it? The idea is you will grab a pixel from the rabbit and you find the corresponding pixel in the same spot in the hat. In general, the hat is bigger than the rabbit. So in order for us to hide this pixel in another pixel, we basically do this, right? So you grab maybe the first 3 bits, like these are the most significant bits from the secret message, and you write them into the least significant bits of the context. And by doing this, what we are basically saying is I changed the pixel in the context picture, but because human eyes cannot see small variations of the color, the context picture will look almost exactly the same. Right, so there's no problem with that. But the most important information of this rabbit is now inside the hat. That's what we have. And then I say, okay, once you have this encrypted picture, the receiver of your steganography will say, I will grab the last 3 bits and I would append 5 zeros, for example. This will be red. This will be green. And then you just append the trailing zeros here. So this would allow us to recover or kind of recreate the rabbit. Any questions about this steganography idea? All right. So For this one, what we can do is we talk about like we did our demo, but the demo is more about not about binary. I just grabbed the last few. I think it's just the last digit of the decimal number, and so we were just playing with that. But um, manipulating data in the binary domain, in fact, it's more nuanced. It's better. Okay. So that's what we'll be doing today. So first thing is we'll look at how to extract information from a number and then how to append it to another number or how to kind of append zeros in the end. Right? There are many things we can try to do here. So that's the steganography. And then once we finish steganography, you should be ready to do PA5 next week, okay, which is about steganography. And then we'll look at dictionary. I think we'll have some time to work on the dictionary idea, and then we'll call it a day today. Huh. So first thing, how do I manipulate binary numbers? Almost every language would give you tools to manipulate binary numbers, and they're called bitwise operations. Because when you try to manipulate the binary number, normally you are processing the number or manipulating it bit by bit. So we'll look at those operations. Okay. The first thing is shifting. If you have a number, you can shift everything to the left by 1 bit or shifting everything to the right by 1 bit. And everything here are operating in the binary domain. Okay, you're operating in the binary domain. For example, if you say, if this is my number, I say left shift 1 position. Then you basically get rid of the leftmost bit, you append 0. If it's an 8-bit number. In essence, you are kind of basically double the number. Because once you append 0, it's like you multiply by 2. If you say I will right shift by 1 position, you get rid of the last bit, you append 0 on the left side. Okay. That's what we have. You have to be careful in here, especially when you do left shift. A lot of times, for other languages like Java or C, normally there's a limit on how big of a number you can represent. That's not the case in Python. In other words, you can keep shifting to the left side, nothing will be removed on the left. You will just keep doubling itself because Python supports large integers. So just be careful. When you do left shift on Python on a number, you in general just append a 0 at the very end. You double that number. Right shift would allow you to get rid of the last bit and append a 0 on the left side. Okay, that's what it is. Okay. Any questions about shifting? So let's look at this one. Right, what is 6 left shift 2? 6 left shift 2. What is the answer for that one? All right, so We'll stop the polling here. Okay. D looks like the most popular choice. If you think about 6, right, it's binary 110. If you left shift 1 position, it becomes 1100. You basically shift everything to the left side, append 0. If you shift 2 bits, which is what we're doing, is 11000, where this is 24. So when you left shift 1 position, you multiply this number by 2. When you right shift this number, you divide it by 2. But shifting is much faster than multiplying or division. So if you say, I just need to double this number, do a left shift. Okay. Any questions about this part? How about this one? 20 right shift 1. What do you think is the result? 20 right shift 1. Remember, all these numbers are expressed in decimal, but all the math is being done in binary. Okay. All right. We will stop the voting here, and we'll stop the vote. Most of us said C, 10. That's correct, right? So 20 divided by 2 will give you a 10. So, and remember, these divisions are kind of integer divisions. Okay, 20's binary equivalency, I think, is 1, 0, 1, 0, 0. Is it? I think that's the binary equivalency of 20. If you do right shift, you get rid of the last 0. You get 1, 0, 1, 0, which is decimal 10. Okay, that's what we have. How about 10 right shift 2? What would you say the answer is? What is 10 right shift 2? Right. We will stop the vote. We disagree with each other quite a bit on this one. A and B dominates. So 10 right shift 2, it doesn't mean it's 10 divided by 2. It means 10 right shift twice. 10 is 1, 0, 1, 0. 1 right shift, remove the last bit. Shift again, remove the last bit. So it's 2. The other thing is it's not 2.5. You can also think 10 divided by 2 is 5. 5 divided by 2 is 2. It's all integer division. So in fact, the correct answer is C. The correct answer is C. So it's not A, it's not B. Like for example, 10 right shift 3 doesn't mean it's 10 divided by 3. It's 10 divided by 2 3 times. Okay, and all the divisions are integer division. Any questions? Now, how about the last one here? Shifting 10 left shift 10 position. What would you say the answer for this one? All right, we'll stop the vote. A lot of us said B, right? In fact, that's the right answer. So Python doesn't limit how big the number is. So 10 left shift to 10 positions. It just 10 is this one, you multiply basically the first one, you multiply 2, you get the 20. 20 times 2 again, you got 40. So you multiply 2 10 times, which means it's 10 times to the power of 10, which is this number. Okay, so just be careful in here. Any questions? So we have left shift to right shift. So what? Right? When do I need it? The idea is, for example, if you say I have this 0, 1, 1, I really want to append 5 zeros to it. You just left shift this thing 5 times. You got it. Right? So it's the same thing for here, it's the same thing for there. If I give you a number, you say I want to append 5 zeros at the end of this number, you just left shift 5 times. If they about when do I need to use right shift? For example, I want to extract these 3 bits. I can right shift this number to the 5 times, and then I just extracted 0, 1, 1 at the very end. That's what we have. Yeah. Any questions? All right, so this is shifting, right? How about just this thing? Just be careful. Let's say x equals 25, x right shift twice, print x. What will be printed out? This is more about something that you just have to watch out. It's not necessarily about if you understand shifting or not. What would you say the answer will be? What is the value of x? Mouse is covered. All right. Let's look at this one. Okay. So a lot of us said it's gonna be A. Let's try, right? I think for those of who said it's gonna be A, it's like, oh, 25 divided by 2 is 12, divided by 2 is 6, right? So that's why people vote for A. Unfortunately, it's not A. When you say x right shift 2, this one is not gonna change the value of x for you. If you want to say this equals to x, you got to say x equals to x right shift 2. Just you have a variable, you say right shift 2 or left shift something, it's not going to change the variable's value for you. You got to assign this result back to that variable. So the answer to this one is still 25. Okay, just be careful. You got to assign it back to the variable. Because we've seen people making this mistake and their logic is right, but it just, my code doesn't work because these variables are never changed. So just be careful on this part. Any questions? All right. So that's the first thing, shifting. Okay, shifting. You can shift to the left, you can shift to the right. It should be all good. Now, the other thing that we can do is bitwise operations. Bitwise operations. Okay. So we have bitwise AND, we have bitwise OR. AND is this AND symbol, or just vertical bar, which is like shift the key right above your enter key. That's the bar. Okay. So when you do these bitwise operations, we are really looking at you have 2 bits and you're trying to generate the output. We in general treat 0 as false, 1 as true. So for AND logic, if both bits are true, the output is true. The result is true. If you have any input being false, the whole thing is false. Okay, that's kind of what we have. For OR, when you have both of them being false, the result is false. But if any of the 2 things is true, the output is true. So they give you different logic. So when do I need something like this? For AND, as you can see, it's very easy to get 0. A lot of times you have something that you have this variable, for example, x, right? You can think it's a sequence of bits. And what I have is, I want to, for example, I want to clear out this bit, I want to clear out that bit. I really want to just keep everything else. I just want to get rid of those bits. Then all you need to do is to say, okay, you want to get rid of these 2 bits, keep everything else unchanged. I can see you end with this number. We call this a mask. It's different from the mask we were wearing during COVID. Right now, I think a lot of you are still wearing masks, which is good if you are sick or if you try to protect yourself, right? So in here, you can do this. This is a bit mask. X end with 1. Anything end with 1 always equals to itself. But anything end with 0 would be 0. Right? So if you do something like this, the end product will be exactly what you want to have. And this is called clear operation. You say, I want to wipe clean these bits to be 0. Okay. Any questions about bitwise AND and what in general we use this for? Bitwise AND is like you have an eraser, erase those bits to be 0, no matter what they are to start with. For OR, as you can see, it's very easy for you to get 1. So for OR, in general, you are looking at set operations. Let me set all these bits to be 1. So we have X, I have these bit positions, and then you say my goal is to say this thing should be 1, this thing should be 1, this thing should be 1. And everything else should be just by themselves. Right? So what kind of mask should I have? The mask I should have is for those positions that you want to end up with 1, you do a 1. For all the things that you want unchanged, just do a 0. And you do a bitwise OR. Because anything OR with 1 would be 1. Anything OR with 0 equals to itself. So this is the idea of set operation. So you can wipe clean certain bit positions by creating a a mask, you can also set certain bit positions to create a mask, and you can pretty much manipulate the bit positions of a number any way you want to with and or and shifting. There are other operations like exclusive or are not. You don't have to worry about that for CSE 8. Any questions about and then or? All right. So let's look at this example. What is the end result of this operation? So 0b means it's binary, and so this binary number and with this binary number, what is the result? Let's vote. Yeah. Vote on this one. All right. So the most popular choice is D. Let's check it out. I think maybe right in here. So you got to line up the bit position. And do an AND. It's bitwise operation, so it's bit by bit. 0, 0, 0, 0, 0, 0, 1, 1. So D is the right answer here. Right? Anything end with 0 equals to 0. Only when two ones end together equals to 1. Okay. Questions about this? How about the next one? Or these two numbers, I think the same two numbers or together. What is the answer?
One question, what does the little dash sign between the two binary numbers mean?
That means or, binary operation or, which is the shift, the key above your enter key. That's how you type it. Okay. Vote in. All right. So we'll stop the vote. Stop the vote. A majority of us voted for B. I think that looks right. So it's 1100 1100 11110000. You are doing the OR operation. Anything, whenever you see a 1, you end up with a 1. So B is the right answer. All right, you do it column by column, basically this way. B is the right answer. Any questions? This is OR operation, not AND.
Okay, so for the OR operation, based off what I am seeing, if it has a one in that direct column, we would put a one at the bottom. And if it doesn't have a one in those columns, we would just put a zero.
Yeah, that's right.
Okay.
Any other questions? All right. So let's do some exercises about like what are they used for, right? So these bitwise operations, we introduce them not for fun, right? They are useful. So for example, I give you so one thing I want you all to know is like Python by default would throw out numbers in decimal for us, right? Because we're humans, so they try to accommodate humans to throw out decimals. But all the bitwise operations happen in the binary domain. In other words, in order for you to fully understand the result, you always have to think in the binary, do the calculations in binary, figure it out, and then convert it into decimal to see if the result is right. Okay. So for example, I give you a red, assuming it's an 8-bit number. In other words, this red can be up to 255, between 0 and 255. I want to take the last 2 bits from this red and return it. How can I do this? Okay. So let me see if we have the lesson Thursday, week 4. Can you implement this method in this challenge? So get to means you want to return the last 2 bits of red. And the other one is this one. So the other one is take the last 2 bits from red. The other one is put the first 2 bits of red 1 into the last 2 bits of red 2. So finish both of them and test your code. Once you are done voting, okay, you have to think, how do I even test my code? Try to finish these 2, or try to finish the first one. If you're done with the first one, give me a vote so I know that you are done. Then we'll work on the first one, and then I'll give you time to finish the second one. Okay, so if you are done with the first one, get the last 2 bits. Right, 2 of us are done with the first one. You just need to finish the first one. Okay. You're done voting. Just grab the last 2 bits. Right. Let's work on this get last 2 together. I think 4 of us are done with it. Maybe I'll give you another 40 seconds. Once it's 4-minute mark, we'll work on this together. It's the first exercise about bitwise. So, we'll go a little bit slower here. Right. Let's look at this one. Okay, let's look at this one. So how do I solve this one? Red is integer. I just need to grab the last 2 bits. So the way that I can think about is you always have to think about, okay, red is a sequence of bit position. I just need to grab the last 2 bits. So it should be an 8-bit. You can assume it's an 8-bit number. So in other words, I need to get rid of these things. They need to be wiped clean, and then I leave the last 2 bits. So this one looks like an AND operation that would do the job. So I can do this. I can say return red and 0b 0 0 0 0 0 0 1 1, and that's it. This would work. So let's say get last 2. How about 255? What's the last 2 bits of 255? Let's print it. Let's not worry about this for now. Okay. And then print get last 2, about 110, right? So let's run this. Python test.py 3 and 2. What is 3 and 2, right? This is not last 2 bits. What does it mean? So if you think about the binary equivalency of 255, let's look at it. Binary of 255, it is this value. The last 2 bits is 1 1. What is the decimal equivalency of 1 1? 0b 1 1 is exactly 3. That's why the last 2 bits of 255 is 3. It's not 55, right? So 255 is in decimal domain. Bitwise operation always manipulate data in the binary domain. How about 2? Like 110. This is the binary equivalency of 110. The last 2 bits is 1 0. 0b 1 0 is simply 2. Okay. So this would give you the last 2 bits of red. Any questions? Is this the only way I can do it? Not necessarily the case. Okay, let me ask you all, would this code also work? I left shift 6 positions, and then I shift it back. Would this code work? A yes, B no. What would you say? I shift everything out and then shift everything back. Then the first 6 bits will be wiped clean. And will this work? A yes, B no. All right, a lot of us saying, yeah, it's gonna work, right? So a lot of us voted for A. Let's check, right? So will this work? So if I run python.py, it didn't print out 3 and 2. It printed out 255 and 110. So it didn't work. Why it didn't work? If you think of 255, it's basically 8 ones. And the left shift 6 positions is gonna append 6 zeros. It's not gonna get rid of the first 6 bits in Python. In other languages, it will, not in Python. Okay. And then the right shift again, so those 6 zeros will be removed. You end up with the same value. It's not gonna work in Python. For those who have taken like Java before, for example, from APCS, you may say, well, in Java it's gonna work out. Java, the answer should be yes, not in Python. Okay, so be careful here. Because Python doesn't limit how many bits you have per number for integers. Any questions about this? All right. No, so this one doesn't work. How about this thing? Would this give me the last 2 bits of red as a mod for? Can you vote in A, yes, B, no? Would this work? It's the remainder of this red divided by 4. Vote in. Okay. We'll stop the vote. Stop the vote. Okay. We have almost a perfect tie. I think we do have a perfect tie between A and B. So the answer is this one will work. This one will work. Okay. So if you run the code, it's going to give you exactly what we had before, 3 and 2. So how come, right? So if you think about this, 255, right? If you think about 255, its binary equivalency is this thing. And 4, the binary equivalency of 4 is 100. Remainder of 255 mod 4 is, if you divide this thing by 4, what is the leftover? What is the leftover? So you can think, in fact, this number as the sum of this thing plus this thing. Right? If you add them up bit by bit, you get that number. This number, in fact, is going to be a multiple of 4. because the last two bits are zeros and this one. So this is a multiple of 4. And this thing is not a multiple of 4. So this is the leftover, which will be the last 2 bits of this number. So that's what it is. So if you say, I'm looking for the last 2 bits, mod 4 would work. If you say, well, how about the last 3 bits? Mod 8. Which way is better though? Is this modulation operation better, or is this bitwise AND operation better? Bitwise operations always win. So this approach will work, but it's not going to be as efficient as this one. Sorry. Okay, this is the best way. Any questions about this? All right. So this is the answer for the first exercise. Now, the second one, how about we, let me see, the second one goes like this. You have red 1, you have red 2, right? You can think red 1 is some, let me draw it in here. So red 1 is some bit positions, and the red 2 is another set of bit positions. So what we want to do is we want to put the first 2 bits of red 1 in here. We will put it in here. In other words, used to be XX, now it's RR. Nothing else would change on red 2. You are supposed to return this result back. That's what you are supposed to return. Okay. So by doing this, you are not supposed to change red 1, red 2. You're just going to return this new result. How about we take a break right now, and then we'll come back and we'll work on this one. But if you come back early, feel free to get started on this one. Okay. Let's take a break until 12 o'clock, and then we'll come back. We'll finish this one together. Okay. So let's take a break. Come back 12. Okay. Come back 12. All right, everyone, get ready to come back. 1 minute. This class. All right, so let's get started here. Okay. So for the second exercise, we want to put in the first 2 bits of red 1 into the last 2 bits of red 2. Well, when you try to do bitwise operation, there's I want to put something into the other spot. The first thing you got to do is you got to align bit positions together. In other words, I must first move these 2 things over here to align with the last 2 bits of red 2. In other words, I need to get rid of these things and move RR here. And this operation, in fact, can be achieved using right shift, right? So you say first 2 equals to red 1, right shift 6 position, for example. Then only the first 2 bits are left. Once I have that, I want to now put these first 2 into the last 2 position of red 2. I need to first make sure that I'm clean. The last 2 bits of red 2, for example, the last 2 bits of red 2 are like here, right? I have the RR with a bunch of zeros in here, right? So this is the idea of first 2. This is red 2. Now I want to kind of replace this X with RR. The way to do it is you can first try to wipe clean these two. And then you simply do an OR operation, then it's gonna work. Right? So you can wipe clean the last two bits of red 2 to get to this part. So basically you can say a temp. Although wipe clean the last two position, you can do an AND with 0B 1 1 1 1 1 1 0 0. This would take care of the last two bits of red 2. And then you simply return first 2 or temp. And this would be the result. So this part is to grab the first two bits, align it at the right spot. This is to wipe clean the last two bits. And then this OR operation would combine them together. Okay. Any questions? There's one question, what does temp do? Temp holds a temporary result. So if you think about red 2 is this, and I AND this thing with this value. Basically, everything in the first 6 bits stays put, the last 2 bits wipe clean. And this is what temp is. Any other question? How about we do this? Put 2 digits, right? Let me change the description. Like what I want to do is the following. I want to put the last 2 digits of red 1 into the first 2 digits of red 2. Can you change this code such that it's gonna take the last 2 digits of this one, put it into the first 2 digit red 2, and then return it? Can you do this? If you can do this, pretty much you understand what we just discussed. If you can't do it, there may be still something that is fuzzy to you. Yeah. If you're done voting, okay, 3 of us have voted in, but think about this. Put the last 2 digits. You always have to think about red 1, red 2 in a binary way. Okay. So let's work on this together, right? So how do I do it? The first two, sorry, what is it? The last two digits read 1 into the first two digits read 2. Read 1 is read 2. See, what did I just say? The last two digits read 1. In other words, I want to put these two things over there, right? So what should I do? Well, first I got to align them, right? I must put these axes in there, and then everything else will be 0. That'll be good. So the way to first I need to get rid of these 8 digits, and then just wipe them clean to be 0. So if you do something like this, the first step is you can say the last two. If I can just call this temp 1 equals to get last two read 1, right? So I already wrote the code how to get the last two. And then I got to make sure that I left shift 6 positions. Right? I must left shift to the last 2 bits 6 positions. Now I'm ready to, so the last 2 bits are aligned with the spot they're supposed to do. Now, for read 2, I got to wipe clean these 2 bits. Before I can AND them to give me the result. So to wipe clean the first 2 bits of read 2, zero B, 0, 0, 1, 1, 1, 1, 1, 1. Right? So this would wipe clean the first 2 bits. And now I'm ready to go. Temp 1 and not AND, or temp or read 2. That's it. So this is to get the last 2 bits, shift the last 2 bits into the right spot, wipe clean the first 2 bits of read 2, or them together to get the result. So it's a step-by-step thing. Okay, you obtain what you want to put from, shift them to the right spot, and then wipe clean the target to AND or to make it work. Are there any questions about this exercise? Okay. So these are the solutions you can see in there. Now, a quick summary of steganography here, right? So you have the context image, which is the picture you will send around. You also have the secret image, for example. The encryption process of hiding the secret image inside the context is, or the assumption is, they must have the same size or the context is bigger than secret. You grab a certain pixel from the secret and the context, they must be of the same location. Okay. So you grab the RGB from here. You take the leading 2 positions of secret for RGB. In other words, you get RGB in here, you get the first 2 bits, for example, and then you put it into the last 2 bits of this RGB for this pixel. And then you are done. You will get this picture. So this picture and this picture, if you look at it, they are basically the same. Human eyes can't see the difference from human point of view, but if you look at the last 2 bits of every pixel in here, it's going to be different from the last 2 bits of the pixels. Now, for the decryption process, what you need to do is you need to first create a blank canvas with the same size as this one. So you create a blank canvas. And for every pixel in here, what you do is you extract the last two positions for each RGB, and then you need to shift them to the left 6 positions. So you don't end up with totally black picture. And then you put it into the corresponding spot in this blank canvas. In the end, this is going to be the decrypted image. If you look at the decrypted image compared with the original one, they're going to look different because for this one, you only have 64 colors. In here, you have 16 million potential colors. So it's going to be different, but you can still see this is the smiley face. Are there any questions? All right. So this is the second RFP, and that's what you need to do for PA5 next week. Okay. So PA5 is about encrypting the image in second RFP or decryption. Okay. Any questions about steganography? We are done with picture processing. We're done with picture processing. For the last topic for this class, for 8A, is about dictionary processing. Okay, dictionary and also CSV files. So I think today we can get started with what a dictionary is, and then talk a little bit about CSV files. And that probably will be it. I don't think we'll work on CSV file today in here, but we'll talk about what a dictionary is. Okay, and next week, I think by Tuesday, we will be able to finish everything for the entire class. Thursday will be mostly Q&A for next week. Are there any questions about picture processing before we leave it and look at dictionaries?
Maybe like after class, if you can't do it right now, but I'm wondering if you could go over the put 2 digits again.
What do you mean the 2 digits? Which example?
The one beforehand, it was the second one. The second function. Yeah, that one.
We can go right now before we move on. So, what's confused you?
I'm kind of wondering what temp. I think temp1 stands for.
I mean, the second example that we had, this code. I mean, this code to put the last 2 digits red 1 into the first 2 digits red 2. Let me give you one example of what temp1 and red 2 really have in here. Let's see. Let's make sure we're clear on this before we move on. So this is the code we have. For example, if red 1, I'm going to say 0, 0, 1, 1, 1. That's red 1. And red 2 is 1, 1, 0, 1, 1, 0, 1, 0. Okay, just making up those 2 numbers. So what I really want to do is I want to put these 2 bits. Oh, they look like there won't be any change. How about this one? So I want to put the last 2 bits of red 1 into the first 2 bits of red 2. Right, that's the goal. So temp 1 initially would, if I call get last 2, it's going to give me the last 2 bits. So it will be 0, 0, 0, 0, 0, 0, 1, 1. The last 2 bits of red 1. And then I left shift 6 positions. Basically, I append a bunch of zeros after 1, 1. That's what I end up with. So that's what temp 1 would give me at this time. Now for red 2, I end red 2 with this value. So anything end with 1 equals resolve. But the first 2 bits will be wiped clean. So this is the new red 2. And I OR them together, 0, 0, and then 1, 1, 1, 0, 1, 0. If I do the OR operation, the first 2 bits are in. The last 6 bits are not changed. This is what it looks like. So hopefully this makes sense now. Any other question?
Oh, that clarified it a lot. Thank you.
Any other questions about this part? These operations are not super straightforward because humans don't think in this way, right? But for the machines, that's what they do. Bitwise operations is always preferred over math. It's just because they're faster.
Wait, so for temp 1, where do you get the 000011 again from?
Where do you think I got this one? It's coming from here, right? Get last 2, red 1. We already wrote this function. Look at it. We're just calling this function to grab the last 2 bits. That's where it came from. Now we just wrote this function. We're just using it instead of reinventing the wheel. Any other question?
Did you just make up a value for red 2?
I didn't make up. Well, this is just an example, right? For red 2. A red 2 can be any binary sequence. Will work. This is just one example I made up, just to show how the code actually manipulated the bit pattern.
Like in the function red 2. So that second part, that's when you made up for that situation, or
Which one? This number 0b.
Yeah.
That's
Yeah.
a mask. That's a mask. That's not a value I made up for red 2.
Oh,
That's a mask I created so I can manipulate red 2. The
okay.
mask and it's just like this is more like I don't know. In real life, what does it look like? So I can't think of any analogy here. This mask is more like a filter. We are trying to filter red 2 through this mask and will only kind of give me the result I want to have. And that's kind of what we have. This is the mask that we used. So is this thing. This thing is a mask. And you make these masks. Right? You make those masks to get what you want to have. How about we do this? How about we do one more exercise? It looks like there may be some questions in here. How about we do one more just before we move on? I think we have some time today. How about define this or call this? I don't know. What's the best way for me to? So I call this get evens of variable x. Okay. What this one really does is gonna return the combined even position values of x. So what does it mean? For example, if x is this, you can think x is a bit number. I have 1, 0, 1, 1, 0, 1, 1, 0, for example. The even positions are location 0, location 2, location 4, and the location 6. So this one should return zero, 1, 1, 0. So the even positions, this bit, this bit, this bit, and that bit. You grab those individual bits and put them together. That's what you need to return. So this one is a little bit trickier, but let's try it. Can you do this? Grab this bit, grab that bit. So all the bit positions, and then you collapse everything. So let me give you an example. So if you look at 1, 0, 1, 1, 0, 1, 0, 1, the locations is location 0, 1, 2, 3, 4, 5, 6, 7. I'm looking at the even positions. Even position 0, 2, 4, 6. So if you look at this 0, 1, 1, 0. Sorry, 0, 1, 0, 1, 1, 1. This is what you want to return. Put them together. How do you do something like this? You can assume x is just an 8-bit number. I'll give you some time. Can you do this yourself? Two of us are done. Let's see. Let's wait one more minute before we finish this up. Okay. You get the bit positions and then combine them together. I mean, this one is definitely harder than the previous ones. All right, so let's work on this together, right? How do I do this? Well, first thing I want to grab the 0th bit, the 2nd bit, the 4th bit, and 6th bit, right? So I say bit 0, X AND with everything else is wiped clean. 0B, 0, 0, 0, 0, 0, 0, 7 zeros, 1. Bit 2 equals X AND 0B, 0, 0, 0, 0, 0, 1, 0, 0. Yeah, that's what I have for bit 2. Bit 4 equals X AND 0B, 0, 0, 0, 1, 0, 0, 0, 0. That's bit 4. And then bit 6 equals X AND 0B. Have some spacing here. Looks fine. 0, 1, 0, 0. And that's it. So I kind of to the end, I grab the individual bit pattern. Now I can't simply OR them together because they are not compressed. So in fact, I want to move this position. So bit 2 now have something at this spot, but I need to move it over there. Right? Just right shift one position. This one, I need to right shift one position to get what I need. And for this, I need to right shift back to go from 4 to 2. Now I need to right shift 2 positions. Now from 6 all the way to location 3, I need to do 3 positions. Now I'm ready to combine them together or return bit 0 or bit 2 or bit 4 or bit 6. And that's it. So this OR operation would combine everything together. Because for these bit patterns, there are just this specific bit that I grabbed. Everything else I guarantee to be 0. So it's going to work out just fine. In order for you to solve these bitwise operations, again, one step at a time. You grab the corresponding data out, shift them to the right spot, combine them. Okay. Questions?
Can you explain why you had to shift them?
Because let me give you the example here. So if I don't shift, bit 0 would have a 1 here, bit 2 would have a 1 here, bit 4 would have a 1 here, bit 6 would have a 0 in there. But in the end, I want to put all of them together, so I got to move this 1 over there. I got to move this 1 over here. I got to move this 0 over there. That's why there is a shifting to move those bit patterns to the right spot, because in the end, this is the value I want to return. If you simply want to return 0, 2, 4, 6 at their original spot, it's much easier. You just need to end the original number with 0, 1, 0, 1, 0, 1, 0, 1. And that would just leave those even positions out, but you need to shift them in the right spot. That's why we have to grab individual bit positions and then shift. Any other questions? For the steganography, you don't need anything fancy like this. I mean, if you understand these, putting certain bit positions from one number to the other, if you know the basics like this, you're fine. All right, then we'll move on. Okay, then we'll move on. So the remainder of today's class will be devoted to introduction to dictionaries. Okay, dictionaries is a structure, data structure provided by Python that would give us a mapping. In other words, dictionaries can give you a relationship between two kinds of data. For example, you can have a name to salary mapping. Given the person's name, this is the salary of that person. Or given the zip code, that may be an integer, you map it to city name. The weight of a person map to the name, or the email of a person match to the GPA, something like this. Right, so give you the relationship between two categories of data. If you think about list basically is a mapping from integers to data, right? We use the index to indicate which cell am I looking at. But dictionary is kind of more universal here. So this is how you create a dictionary. Show you. So dictionary, you have a variable name equals to the curly bracket. Curly bracket indicate is a dictionary. Okay. You have the first kind of data, we call this the key. Column, we call the second part is the value. Key in general, it means in CS, key means the thing you look for, the thing that you look up. It's like when you look up a dictionary, you want to know what's the meaning of this word. The word you're looking for is the key. The meaning of that word is the value. Okay, so in other words, normally if you have a key value pair, the key is the one that you are looking for. So you want to know what is the GPA of Paul, 3.14. What's the GPA of Christine? It will tell you it's 4.40. Right? So in general, you don't say, hey, whose GPA is 3.14? That's not what you do. You always look up the key and you get the corresponding value, not the reverse operation. Okay. So if you think about dictionaries, they are objects. So if you have a dictionary in here, this is an object in the heap. So you have a Paul map to 3.14, Christine map to 4.4. And you can use a dictionary to look up the value. In other words, if I say dictionary Paul is in the square bracket, it will tell me 3.14. This one would give me the value of Paul, which is 3.14. Any questions about this part? Right. So let's look at this one. Number one, can you create a dictionary that stores this data? This is the salary of three people. Pao Chao, Mian Minus, and Record. This is the annual salary of these people. Record have to pay us to work at UCSD. Record is a faculty that retired recently from the department. But Mia and I are current faculty, so assuming these are the salary of all the people, can you create a dictionary by yourself? Just grab a piece of paper, write it down how to create a dictionary. Once you're done, give me a vote. Um, so let's just write this together, right? How to create a dictionary. Let's say you can call it anything you want. It doesn't have to be dict. It can be salary equals to a curly bracket. Say PC. The salary is 1, 2, 3, 3, 4, comma. Mia minus. Her salary is 3211. And then record. The salary is -5. Right, so it's the key value pair separated by commas. Then this dictionary will have 3 things there. Okay. Any questions about this part? How to create a dictionary? All right. How about this one? I created a dictionary. This is a zip code to city name mapping. 92122 is San Diego. This is the UTC area. Okay. And in fact, in the United States, there is this zip code 12345 for this interesting city called Schenectady. It's a city in Jersey, I believe. And 92093 UCSD has its own zip code. UCSD is like a small city. It's getting bigger and bigger. So these are the 3 entries in the dictionary. And if I do something like this, what do you think will be the answer? Let's click on the wrong button. Here we go. Promoting. There we are ready. Right. Let's stop the vote. A lot of us voted for A or D. A looks like it's going to be Schenectady. D is on the error. In fact, D is the correct answer here. The how come Schenectady is not given? Because 1, 2, 3, 4, 5, this is integer key, and you are passing in 1, 2, 3, 4, 5 as a string. The map is not going to say, well, give me a string, I will convert it into int first. No. So if you say zip code 1, 2, 3, 4, 5 as int, it's going to return Schenectady. But other than that, it's going to treat 1, 2, 3, 4 as just a key you want to look up, and it says I don't have this string as a key inside my dictionary. Okay, so just be careful. The key must be the exact same data type, and it has to be exactly the same as the key that you're providing. Okay. Any questions? All right, how about this one? This is the same dictionary. I say zip codes UCSD. What do you think will return? what will be the result? Stop the vote. A few of us said C, most of us said D. Again, D is the right answer. Why is not 92093? Because this is the key. Maps can only look up the key. You cannot do it reversely. So it has to be the key in the square bracket. If you say square bracket UCSD, it's gonna say, oh, well, UCSD is not the key that I have here. It's not gonna say, oh, is it one of the values? Nothing like that. Okay. So the answer is error, key error. If I say zip code 1, what do you think will be the output? If I say zip code 1, the same choices A, B, C, D. What's gonna happen if I do that? All right. So the answer, a lot of us said A or B, is going to be San Diego or sorry, is going to say 9122 or 1235. The answer is still D. The answer is still D. Because it's going to treat 1 as a key. Do I have a key that is 1? The answer is no. You're still going to see an error. The error message probably will be different. It's like the key 1 is not found in the dictionary. You cannot use index. No index is allowed for maps. Every data of a dictionary, it says. So all the data are accessed using the key. There is no index. There's no index. Questions? All right. How about this one? And I'm doing this, so the same dictionary, and then did something weird. And how about this? What do you think the output will be? And then we'll take a small break. Let's see. Right. So it looks like people are gonna say, oh, most of us said D, in fact. Okay, so we'll stop the vote. The answer is correct. So D is the correct answer. So you used to be the zip code. The D is the right answer. So when you do something like this have two functionalities. So zip code used to be 92122 maps to San Diego, 12345 map to Schenectady, and then 92093 is UCSD, right? When you have zip codes 1, 2, 3, 4, 5, you basically say, oh, I have this key here. And you are basically updating this Schenectady name. Schenectady is Tall City. This is an update. But if you say, I don't have 1, 2, 3, 4 before, what's going to happen? It's going to create a new entry into the map. That's the difference. So this part have two potential usage. First one is to update. Second one is, so if the key already is in the map, it's going to do an update. If it's not in the map, it's going to insert. That's what we have. Okay. Any questions? All right. So we'll stop and take a break now. Okay. We'll come back at 1 o'clock. We'll finish up a little bit more. I think once we finish this exercise, we'll stop. So let's take a break. Come back 1 o'clock. Okay, come back at 1. All right, everyone. Let's get ready